Now let's continue from where we stopped. The last question says, before we call it a day, yesterday morning, is this a missile weighing 400 Newton on the Earth's surface? It's shot into the atmosphere, altitude of 6.40 times 10 to the power 6 meter, taking the Earth as a sphere of radius 6.4 times 10 to the power 6 meters, and assuming inverse square law of universal gravitation, what will be the weight of the missile at the altitude? To solve this, what we do is simple. So the first weight we have here, weight 1, we take it to be F1, and that's 400 Newton. At that time, the radius is equal to 6.4 times 10 raised to power 6 meters. The second one, weight 2, unknown. That's F2 that we don't know. Now, we now have this R1. R2 now, we give you, since it is at the altitude, it's like this. The Earth is like this. That's radius R. Then something is now above it. So that one will have its own circle around the edge of it, having another R. So it's now above it here. That guy, that's thing, the missile will be up here like this. So which means that the R2 will be what? Will be 64 times 10 raised to power 6 plus 6.4, sorry, times 10 raised to power 6 again meters. You can see that it's just like 2 times. It's just like this guy is like 2 times R1, or we say 2R1. Then from there, what we know is that F, if you write the whole formula, our F ordinarily is equal to M1 GM1 M2 all over R squared. So which means that, let me remove F1 here. It means that F is indirectional to the square root of the radius. So in this case, what do? We just say that, okay, what we have here is F1 is, from here, let me just say that, okay, this one is constant. So we just say that here, F is equal to K, where K will now be equal to all these M1, M2 over R squared. So we have F R squared equals K. This means that F1 R1 squared is equal to F2 R2 squared. So from there, we want to get our F2 and see what that will be. So F2 now will be what? F1 R1 squared all over R2 squared. In essence, what we are saying is that we have F1 to be 400 times R1 squared. I don't want to use the figure again. That's 6.4 times 10 to the power 6. I don't need it. So we'll now write 2 R1, then square everything. The meaning of this is 400 times R1 squared, all divided by 4 R1 squared. R1 square cancel R1 square, this one cancel this, cancel this, this cancel this. We have 100. So the final answer here is 100 Newton. If it is mass, so mass will now be divided by the G, and that will be 10 kilograms. If it is like that. So that is for that one. Now the question says that a body is projected from the Earth's surface with the intention of letting it escape from the Earth's gravitational. What is the minimum escape velocity? So this one here is quite easy. Since they said escape velocity, minimum one, escape velocity here is always equals to square root of 2gr. And with this one, our g is always 10 meters per second squared. And our r is always 6.4 times 10 raised to the power 6 meters. So if you do that, we'll just say that is equal to 2 root 2 times 10 times 6.4 times 10 raised to the power 6. That's the minimum we can get. The radius can increase, but the minimum is it is on the Earth's surface. So with this one stated here, we'll be having what there that will be giving us. Look at it very well. We'll be having 2 times 64 times 10 raised to the power 6. That means it will give you 128 times 10 raised to the power 6. If you do this one well, square root of 128 will be 11 point something like that. 11 points. What's that one going to be? I think 9. I think 9 or so. Times 10 raised to the power 3 meters. So with that, we usually write it as that's the minimum, say 11.9 kilometers. Yes, that will be solved. We need another question. A stone is thrown vertically upwards to the ground. What is the velocity time graph? Now, this question, the way it comes, if you want to know the velocity time graph, the way you have it is this. You have the velocity time graph. You have this place representing velocity. This place. This vertical one is for velocity. Measure in meter per second. Then you now have this horizontal for time. Time measured in seconds. As the body is thrown upward like this, let me draw that one. It's thrown from the, let's say here is ground level. It's thrown upward with a velocity upward. On getting to the top, it will stop momentarily, but not noticeably really. So the velocity there, final velocity at that point becomes 0. So on turning back, it will start with another initial velocity equals 0, while it will end here with a velocity that is very high. The velocity with which it starts here, u1, is the velocity with which it will end here. This v2 here will now be do one, it gain the same velocity. As it's going up, it's decelerating because of the influence. It's decelerating, all because of what? The influence of the gravitation on it. So that one reduces its velocity. So it is retarding until it stops and has final velocity of 0. Then coming down, it will now gain another velocity, but it will start with 0 that it finished with initially. So it will now come down with acceleration of gravity, gain acceleration and increase till it gets to the ground, its final velocity. So if I now put that together, it was initially at the top of the velocity, is retarding, and come to 0 at the upper level. Then later, it increases velocity again, and go like this. It'll get to the maximum velocity again and drop. So that is the velocity time graph of a stone thrown upward, return to the ground. Yes, the question from Somto says that a transformer supplies 15 volts from a 220 volt mains. The transformer takes 0.7 amps from the mains when used to light three lamps connected in parallel and each rated 15 volts, 40 watts. Calculate the efficiency of the transformer. 2. The cost of using it for 24 hours at 30 kobo per kilowatt hour. Now this one here, what we have here as a supply is here. What is the supply? Ordinarily, the total EMF that we add from that place, total EMF that we have from that place is what? E. E equals, why now? E here equals, hope I'm recording. I don't want any pop-up. E here equals, that's the total, 220 volts. But the supply really is 15 volts. You have the current equals 0.7 amps. Now, they said that from what we have this guy here. This is what is being supplied to us. This is what is being supplied. Now, and they are arranged in parallel. Total power produced there, total power produced, PT there produced. You just add the three together, 3 times 40 watts. That is 120 watts. So don't waste our time on that one. Then they say we should find the efficiency. If you are looking for efficiency here, you use the main source, not the 15 volts produced. So the main source is what? Is 220. Is that okay? So here, the overall power that we have is what? That's total power input. That will be IE in this case, which is equals to, when you come in, you mute yourself. Not that you come in and be making a noise. And blessing. And that will give us what? What's that? 0.7 times 220. And then if you look at that, that will be 154 watts. So the efficiency now is what? Efficiency in this case. efficiency with the power output, that's PT that we get there, over P times 100%, which is what? 120 over 154 times 100%. Yes, who has computed that? Who has done that?
77.92.
77.92%. So that is on that one. Then they ask for that's number one. Number one is that. Number two is that they say that what is the cost for running it for 24 hours at 30 kobo per kilowatt hour. So now let's look at the energy produced here. The energy produced here is IB. Okay, we don't even need that. It's just PT. They gave us the time, which is 24 hours, and we convert it. We need to leave it like that, yes. That will give us the energy now will be 120 that we calculated the other time times time. That's 24 hours. So if you multiply this together, that will be 2 times 144, which is 28880 watts hour. Or in 10 minutes, this thing will stop. You know, it's always 40 minutes interval. So in 10 minutes, when it stops, you relog in. So that thing here is equal to 2.88 kilowatts hour. Then since we're told that 1 kilowatt hour equals 30 kobo. Then we can say that 2.88 kilowatts hour equals 2.88 times 30 kobo. Who has computed that? That would be 28.8 times 3. Who has done that? Who has done that? Nobody.
86.4.
86.4. 0.4. 86.4 that we have here. So that is what we have. Okay, that's just it. 86.4. Now that is on that. Now this is a question there. A bird received the echo of his clap reflected by a nearby it 0.8 seconds later. How far is he from the hill? Now this one, they gave us time for 0.8 seconds. We know the velocity as 340 meters per second. We have to calculate distance. This is what they call echo. Now, echo is just that the formula is velocity equals to x all over t. So in this case, 2x equals vt all over, vt. So x equals vt over 2. Why is it like this? Let me give you explanation on that. Why the formula is like that. Let's say this is the hill here. The guy is standing here. He claps here. Then that sound will go through a distance x. It will come back again through the same distance. That's why the x is 2x. Is that okay? So now we have 340 times 0.8 all over 2. So it's like we have 34 times 4. And that will give us around 136, I think so. 136 meters. Okay. Okay, I think so. Now, from blessing, the question says that an air bubble rises from the bottom to the top of the water dam, which is 40 meters deep. The volume of the bubble just below the surface is 22.5 cubic centimeter. Find its volume at the bottom of the dam if the atmospheric pressure is equivalent to 10 meters. Now, this question is talking about the pressure here. We are dealing with pressure here. How do we solve this? It's simple. Now, we have something we call below the surface and above the surface of the earth surface. This is the, now, the sea level is also the same level with what? With water, with sea, with the land to say. So, hope that is not. Now, this case, here is the ground level. Ground level. Now, the atmospheric pressure is acting on the ground level. That is H. So that's one. I will call it P1 or P2. Anyhow, okay, let me make it P, which is 10 meters. Now, below the ground level, the level of the dam as the sea is also the same level with the ground level. So that one is below, is 40 meters below, 40 meters below. That is small letter H to say. So here, I will say that we have P1 here. And that P1 will give you H plus H. The pressure increases with depth. And that will give you 10, which is the atmospheric pressure, P1, P2 plus 40 here. And so the answer now will be 50 meters at that point. At this point also, the volume V1 is 2.5 cubic centimeter. We are looking for the volume at the top here. We just use Boyle's law to say that V1 equals P2 V2. We are looking for V2. That is P1 over P2. The answer now will give you P1 is 50 times 2.5 divided by 10. This cancels this. So our final answer is 12.5 cubic centimeter. Again to record. I said pressure in the fluid deals with density, height, acceleration to gravity. Then we talk about the pressure. So this one, the pressure here, P is known to be, there's no time to be proving the law now, the formula, rho Hg. That's the formula for the pressure. Now, we now have special cases. If it is, we have the pressure on the Earth's surface or on the sea level, we take them to be on the Earth's surface. We take them to be the same thing, that they are the same level. If it is on the Earth's surface, let's say it is ground level, the ground level, or sea level, they are the same thing. So the pressure here, let's say it's P1, is always capital letter H. That is the pressure acting on it like this. And it's called the atmospheric pressure. The pressure on the Earth's surface by the atmosphere. Now, the second thing is pressure above the ground level. pressure above the ground level, their noise. So we have pressure above the ground. Above the air surface, same thing as above the ground level. Is that okay? You take the air surface to be what? To be the ground level. It can also be water surface. No problem. So in this case, let's say air is the ground level. The ground level. For it to be a height above the ground level of small letter h, let's say h2. So the pressure that will be above the ground level here P2 will be h minus h2. Is that okay? Let me now take the pressure below the earth surface. Below the earth surface. If it's below the earth surface, if this is the ground level, the ground level. So we have our h here ordinarily, just like we add the h here. As it is going down the level, going down here, the height h, let's say h3 now. That will give us a pressure down there. The pressure increases with depth. So this P3, that will give you H, the height is the pressure at the is there. Now it's not going down. That means that it's pushing it down. Give it H plus H3. Now let's now go to manometer of a thing. If it is manometer, let's see what happens. When you use a barometer or manometer anyhow. Let's say we have, what is that? So just coming in, please mute yourself. Barometer or manometer. How do we get a simple barometer? That is what is quite easy to use, even with manometer. What we do here is we have a beaker and there will be mercury inside it. Then what's it called? A test tube is inverted down there. So this is the level outside. Ordinarily, the first thing it will do is to rise. Later, it will drop. So later, we have the height here. That height that you have is a measure of atmospheric pressure. The H you get here is a measure of atmospheric pressure. You calculate letter for it anytime. Now, what now happens? If you now have a U2 or J2, let's say we have U2, a tube in form of U, like this, like this. When you pour mercury air and the mercury now flow to this side, they will settle at the same level. Same level. The level you have here is what you have at the other side. And that will signify the height of the atmospheric pressure. the height of the atmospheric pressure without any influence. Without any influence. This height you get here is the atmospheric pressure you are getting. If you put H there, anyone you put there is this atmospheric pressure. So let me put H there, capital H there. Now, if after that, we now decide to use, even it is J, let me use J2 now. J2. You see the same thing. And we have J like this. Who is that making noise now? Ah, mute yourself now. Don't let me strike you out. Oh. Is Annette? Mute now. Be careful. Please come on. Please come on. There. So now here. Okay. Permit my drawing, please. When you pour the mercury air down there, they will settle at the same level. They will settle at the same level, signifying the height of the atmospheric pressure. H. Now, after that, if a manometer is now attached to it, let me now go there. I will use J2 because that is easier to see. Now, this thing was like this before. Together, the two of them, same level like this before. We now attach a gas, maybe manometer. Gas is attached there, gas supply. Atmospheric pressure is acting downward like this. That's the way we always say it. H, atmospheric pressure acting downward. And that's the measurement we made here. Atmospheric pressure acting downward. Use calculator H. When that now happens, we now attach what there? We attach the gas there. We now see that this thing push down, push up against the atmospheric pressure, maybe up a bit with a difference of a height of small h here. This one means that the gas pressure is more than the atmospheric pressure by what? A height of small letter h. Let me use H1 for it. But if it is not like that, if after attaching the something, if after attaching it and the gas supply is still there, let me say gas pressure 1. We now find out that it was like this before, level, then atmospheric pressure acts downward like this. But this thing now rise up at the side of the gas by a height of H2. It means that atmospheric pressure is greater. That's why it's pushing against the gas, pushing it up. It means that the gas pressure here, gas pressure 2 now here will be H minus H. Is short by the H, small letter H2. Yes, let me use H2. Then the last thing we need to discuss here is talking about find 2. What happens there? A 2. That is the next thing we need to discuss here. Just a small tube, inverted tube or anyhow. Okay, someone said, can we get the formula for linear magnification of focal length? Now let's go. We have, I'm still on something. I said tube, the simple parameter of a thing. Simple parameter. Talking about a tube now. When the tube, the first case we are taking here is tube with open end upward with a mercury thread and trapped air. In this case, we have our tube like this. Please don't mind my diagram. The thread is air and air. Air is air. Air is trapped there. So this is the length of the mercury, H to say. And from air to air is the length of the air, L. This is H is what? Length of the mercury. While this one is L, which is length. Or at times they say volume. It depends. Of air that is trapped in that place. Let me use L1. In this case here, once you see the mercury moving up, it's as if the one we did here, this one here, this exact one, it's as if the air is here, you just put it under air. So it's now pushing this mercury up there. So that is what we are doing here. It's pushing the mercury up. In this case, our pressure. So we have a cross-sectional area is there. Cross-sectional area. So in this case, we have pressure P1 equals H plus H. Don't forget that atmospheric pressure is acting downward like this. H plus H, and that thing is pushing against atmospheric pressure. Then the volume P1 will be AL1. Number 2 of this case. Number 2 here. Number 2. Inverted tube. Inverted tube. In this case, it means that we have a tube inverted. Tube is inverted like this, and that will give us this over this. So here is the mercury thread length, while this is the length of the air trap here, L. So in this case, the pressure here, you see that the atmospheric pressure is acting downward, pushing against this guy. So it's pushing it down. So that will give you H minus H in this case. while the volume V2 here will be AL2. What we use in this case most of the time, in fact, every time is a voice stop, nothing else. So number 3 is horizontal 2. Horizontal 2. In this case, 2 is down like this, like this. This is the mercury here. So here now we have our length of the mercury. Here is the length of the air trap. The atmospheric pressure is acting this way down there. So here our P3 is equal to H because it doesn't have effect on the mercury in this case. So the volume V3 is equal to AL3. So that is the summary of everything you have under pressure I've given you. Is that okay? Now the person that asked about the magnification, can we get the formula for magnification, for linear magnification of linear magnification? Oh, yes. Now, can we get formula for linear magnification? That one is simple now. It depends on what you are asking for because I don't know what really you are asking for the mirror or for lens or for other ones. I don't know. But anyway, the linear magnification is simple. Linear magnification. For mirror, we use M really for everything. So it's always image size or height of object size or height. In another place, we say it is the camera length or image distance. That's when we use film camera. All over what? All over the object distance. And the image distance is V over it. Now again, since you put focal length there, whether it's for lens or anything, or mirror, we use mirror formula to be 1 all over F equals 1 all over U plus 1 all over V. Now to get, especially when you're given the, what's it called? You're given only the U and the F. What do you do in this case? And you want to get the magnification in this case. That's quite easy. What you don't do is to say that all you are given only B and F. Anyone you are given, just multiply by what you are given throughout. Let's say let U and F be given. There. Just say that multiply by U always. U over F equals what? U over plus U over. And from there, you'll be talking about what? U over F equals 1 plus U over. So in this case, we are saying that we have U over V equals U over F minus 1. You do that very well. U over V is equal to U minus F over F. And our magnification that we are looking for is V is what? V over U, which we turn this into F over U minus F. If it is V given, that means you'll be saying that you multiply V given. V given. You know, here now, I don't need to do V before I get the answer. So I'll just use my formula here straight and get my answer. F over U minus F over 2. So here now, if V is given, you just see V multiply 1 over F, V over F equals V over U plus V over
So
V.
why did the one change to U?
Which one?
The one like the 1 over F equals 1 over U plus 1 over V. Why did the one change to U?
I said when you are given U and F, and you want to get multiplication straight without wasting time, multiply everything by U, U times 1, U times 1, U times 1. You see that everything is multiplied by U. Is that okay?
Okay, sir.
So if you are given V and F here, to multiply everything by V again, the same thing process I'm doing here. V over F equals V over U plus 1 here. So here we have V over U equals V over F minus 1. You can see this. So in this case, our magnification in this side here is F over U minus F. That's the opposite here. Magnification here will be V minus F over F. If it is V, it's V minus F. If it is U, it's F over U minus F. So that means that we go to new thing here. New thing here. Okay, we're given this by blessing. Let me see whether I've covered that side. Blessing, we have this question from R that says that in a J2, the question says that in a J2, Y and X are on the horizontal level. Y on the same horizontal level. I'm afraid it's the next 10 minutes. On the same horizontal level are 30 centimeter cube of air trapped above Y when 50 centimeter mercury is now poured into the bin above X. In a J2, atmospheric pressure is acting downward like. Now they said in the J2, Y and X are on the same horizontal level. We don't know where Y is VIX is maybe this side or this side. But they said that 30 centimeter air is trapped above Y. Okay, this is Y here. Y is here. 30 centimeter cube. They give us the volume. B equals 30 cubic centimeter. Now we have the mercury here. And when 15 centimeter mercury is poured into the limb above X, so the H here is 15 centimeter mercury. Then what happened? No question at all. A column of air, that's the next question. We have about 5 minutes to end this class. A column of air 100 centimeter long is trapped in a tube at this. What's the length? What is the length of the volume at 100 800? Okay, let me quickly solve this so that we can be happy. So the first one, we have B equals 100A. You use your A even though you are not given the positional area. I mean, then we have C1 equals 27. You add it to the 273, making 300 Kelvin. Why B2 unknown? That length, you just say that it is okay, let me go. C2 is equal to 100. Is 100 plus 273, and that's 373 Kelvin. So B2 will give you AL that you are looking for. But you use Charles law now. Charles law. B1 over T1 equals B2 over T2. So that will give us B1 is 300 all over 4. Sorry, is 100A over 300 Kelvin equals the V2 we don't know over 373. So 0. This one is A L2. A cancel A. 0 0 0 0. L2A will give you 373 over 3. 3 in 3, 1. In 7, 2. In that one, in that guy, that's 4.333 cubic centimeters. So that's on that one. Now, blessing. The question is not.
Hey, sir, they said we should look for the volume for that first one.
Volume.
I'm looking for the volume.
Volume of what?
It said in the J2 below, Y and X are on the same horizontal level.
You said below. That means there's a diagram.
Yes, it's a diagram.
We can't see the diagram here. Who give us diagram? That's why I was confused at the time. That what are we saying here? Is my diagram the same with what they drew? I put X
Yes,
there.
sir. Yes, sir. They put X by this side. Yeah, yes, sir.
X this side, right?
Yes.
Okay. They said that in the J2, blah, 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 the same level, 30 centimeter above Y, when 15 centimeters now fall into the lane above X, was the volume. Abi? Is that?
Yes, was it? Yes, that's the question.
So in the first case, we have P1. That is when they didn't pour anything. We have the same level for Y and X. So our atmospheric pressure is H at that point. Did they give you atmospheric pressure? They should give us. If not, we won't be able to solve anything here.
75 centimeter Hg.
Can you imagine?
I don't see this, sir.
75 centimeter mercury. 75 is given to us. Why B1 here is 30 cubic centimeter. In the P2, this thing has increased by small letter h. At that point, we'll be saying that it's going to be what? You increase it by 75, you add 15 there, and that will give you 90 centimeter. We're looking for P2. So P1 equals P2 copy 1 V1 over P2. Our answer will now be what? P1 is 75 times 30 all over 90. 30 here, 30 here, 3 here is 25. The final answer is 25 cubic centimeter. We have less than 1 minute. I wouldn't know what to do now. And we still have more questions here. Are you coming back for it, or we just call it a day? This question that says that the focal length of a concave mirror is 2 centimeters. F is 2 centimeters. Then, if an object is placed 8 centimeters from it, that is U equals 8 centimeters. The image is at where? V, image distance unknown. But all we know is that 1 over F equals 1 over U plus 1 over V. 1 over V here is equal to 1 over F minus 1 over U. That is to say, 1 over V equals what? Equals U, what am I doing here? I don't need this. 1 over V equals 1 all over 2 minus 1 all over 8. 1 over V is equal to 8 here. Here is 4 minus 1. 1 over V equals 3 over 8. V equals 8 over 3 centimeters, which is 2.67 centimeters. Now they say that a current of 20 amps, current equals 20 amps, flows through a cable of resistance 5 ohms. Calculate the electric power distributed, P unknown, but P is known to be I squared R, which is equal to 20 squared times 5, which is 400 times 5, and that is equal to 2000 watts, which is 2 kilowatts. Okay. Record this thing. Let me record it. You see the focal length there, just like I solved it, that focal length is 2 centimeters. If an object of is placed 8 centimeters from it, the image is attached. So F is 2 centimeters, U is 8 centimeters, V equals unknown. But we know 1 over F equals 1 over U plus 1 over V. 1 over V equals 1 over F minus 1 over U. Doing that, it means that we have 1 over V equals 1 over 2 minus 1 over 8. If you do that, the LCM is 8. 2 in 8 is 4. 8 in 8 is 1. That's 3 over 8. So V equals 8 over 3. And that's 2.67 centimeters. Now, this last question just solved now is, okay, a current of 20 amps goes through a cable whose resistance is 5 ohms. Calculate the electric power. So that's one. I is 20 amps, R is 5 ohms, P power unknown. For P equals I squared R, which is 20 squared times 5, 400 times 5 is 2000 kilowatts. The last question solved now is an alternative circuit question that says that another source is connected in series with a capacitor of capacitive reactance. Capacitive reactance of 10 raised to power 3 root 3 ohms. And a resistor of resistance 10 raised to power 3 ohms. The impedance of the circuit is dash. So XC is 10 raised to power 3 root 3 ohms. The resistance is what? Is 10 raised to power 3 ohms again. So I didn't put the ohms there. I didn't put the ohms so that we can be happy. Ohms there. So this impedance is Z, that is unknown, which is the square root of R squared plus AC squared. So we have 10 raised to power 3 squared plus 10 raised to power 3 root 3 squared. That's 10 raised to power 6 plus 10 to the power 6 times 3. We manipulate to get it there with 4 times 10 to the power 6. Then we got 2 times 10 to the power 3 ohms or 2000 ohms. Question, please. Question.
Second,
Yes.
not that super. What are we going to meet? That's light wave. I don't understand it.
Which
Don't you
one?
thought it was
Which
light
one?
wave? Usually rays, ray reflection and refraction. So I don't understand anything in that light wave.
You mean the reflection
Ray diagrams.
ray diagrams? That's quite easy. It depends. Now, let me quickly discuss the aspect of the reflection that you had issue with. So it's quite easy, really. So, like yesterday, I was discussing something. I've discussed the radius of curvature, many things discussed, really. Let me go to that place where I can still.
Sir.
Yes.
9 o'clock is not convenient for me because my mom is going to take the phone by 8 because she's going to work. That's why I'm
when are you
using
writing your examination? You can get the video at any time.
Tomorrow.
Tomorrow again? Who is that?
Temple.
When
Tomorrow by 3. By 3.
The two of you writing the same time? I think Blessing said 3 now, right?
Yes.
The two of you.
Yes, by 3.
So what are we going to do? Your mom will collect the phone by 8.
Maybe 8. Yes.
So what are we going to do now? Anyway, let me discuss this one and finish it so that any other question you have, you can send it to Telegram or send it to me directly. Then I will give it to you. Then Temple, don't forget to send your phone number so that I can send the YouTube straight to you. Since you are not in Telegram.
Sir.
Now I've explained the concave and convex of a thing. Then focal length explained, everything explained. Actually, the principal axis is this line, these lines that combine the C, F, P together. How do you not draw a ray diagram? It has rule. Once you get the rule, that's the end. If you get the rule easy, that's the end of the whole thing. Now, how do you draw? The first rule that you must note is that rule of ray diagram. Rule of ray diagram. The first rule is that all ray parallel to the principal axis reflects back through the what? Through the principal focus. How do you draw that? Assuming you have this. This principal axis is an object. This principal focus. If an object is here and there is a ray from there parallel to the principal axis.
Is it eating tomato?
Temple, you are disturbing. Mute yourself. So when the ray is drawn, that's the first thing. A ray must be drawn parallel from the object. Then you draw it back through the principal focus. That's the first thing to be done. Second thing, all ray through the principal focus, just like opposite of what we did. Reflect parallel. Reflect parallel to the what? To the principal axis. If the ray now passes through the principal focus, it will reflect parallel to the principal axis. For instance, like this. You have the principal focus here. You must draw another ray passing through the principal focus like this. See the arrow is going down through it. Then you must draw it parallel, again parallel to this line, Then the third one is per absence, a ray through the center of curvature. Reflect along its path. That is, it reflect back along that same line, same direction. That's on this. You see it. Center of curvature is there. Now see an image, something passing through that guy. It passes through the C, then it shortens it. That can go like this. It goes through C. It will reflect back along that line immediately. It will pass through. That is how to draw the diagram. We now combine all this together to give the diagram of anything you want to draw. Let me just give you like 2 or 3 diagrams. Now, the first one I want to do image, nature of image. Of the concave mirror. Once I'm able to draw all this for you, you will get the meaning. Is that okay? Now this one here, we start with the first case is where this is. Number 1, if object is beyond C, that is, you have F here. Let me use focal length now. These 2F or either C. Okay, let me use the principal focus. And the object is here. The first thing you do ever is to draw a parallel line to this place, to the principal axis. And that parallel line will reflect back along F like this. Let me draw this thing to be longer or bigger to see. You see that? See that? So we now have another one that is drawn through the principal focus again, then it will reflect back. Oh, diagram is totally wrong. Sorry about that. Let me just clean that one. Because something is not straight to my understanding. So let me straighten it well. It's drawn straight like this. Then that is the direction. It will reflect back parallel to the principal axis. You can see the way it reflects back. Where they now meet, you will draw your image down to it with arrow towards the place of point of intersection. You can see the object here. See the size of the object. See the size of the image here. This is the O object here. This is the I image here. What does it give us? It gives us real image. Once the image is formed in front like this, in front like this, it's formed in front like this. You say it is real image. So we have real image. We use R for that. Then the image is pointing downward. It means it is inverted. Inverted I. Then at the same time, it is smaller than the object. You say it is diminished. At that point, you have, so we call this one read. Read. Number 2 is object. Oh, now image formed at where? Image formed. Oh, this thing is recorded. It's recorded. Thank God. Hey, it remains 10 minutes. It remains 10 minutes. Oh, sorry about that. Image formed between
C and F.
C and F. You can see that. Another one is object at C. When object is at C, what happens there? So we'll see it now. Tempo, 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 moves, 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 moves. So if object is placed at C, you first draw your parallel line to the principal axis. Then it reflects back along the line to F. You draw again through F. It reflects back to that place. The arrow back. Consider F is important here. So the image is downward here. The image is downward here. You will now see that the normal thing that happens here is that the image is formed in front where you have the mirror. The image is real image. R again is inverted. I again. But it's same size. Same size. That's S, we call it race. So here, image formed at C again. Image formed at C. The next one, you have less than 8 minutes. Then objects between C and F. Between C and F. We have it like this. This F here, C here. Object is between C and F. First, parallel line to the principal axis passes through the F. Through F. Then another one is going through the F itself. It reflects back there. And they all meet. They met here. So what is that implication? The image is still real. Image R is still inverted. I, but it's now magnified. Image, see, look at the objects, look at the image. Is magnified, that is bigger. That is real. Here, image formed where? Beyond C. Image formed. You can see the correlation between the first one and the third one. When object is beyond C, is formed between C and F. Now, object is now between C and F, is formed beyond C. So they're like opposites. So you must get that right. Now let's look at object at F, object at F. Object at F, yeah. If the object is here, we have this guy going this way, parallel. It reflects back along F. Now, another object, instead of it passing through the F, it can't pass through F now. It will pass through C. It pass through C. Sorry. Through C like this. It will pass through it. You know, I told you anything that passes through C will reflect back along this line. Reflect back like this. So passes through it like that, it reflects back in that line. So, and that is why you see the image can be seen here, but it's formed at the infinity. The image is still real. It's said to be inverted here, even though we can't see it because it's going down. We can't say that it is the magnifier. Nothing we can say about that. It's just RI there. Then image formed at infinity. The last one for this one is you go and master that of the what's it called? That guy, the complex. It's just one. Give you virtual image, diminished, direct. That's always sure for that one. Let me now take the last one here, number 5. It remains just 1 minute 50 seconds. Objects between F and P. I need to rush this one because of time. We have F here, P here. I didn't show PC. C here, object is here. So this guy here goes like this. Instead to pass through this guy like this, but it reflects backward. It appears at the back. Outside there. Less than 1 minute. So this one also goes like this to C, or reflect. I can join it together to C, or reflect backward like that. There, outside goes this way to C, or reflect backward like that. Then the next somewhere around here in front. There. So the image is virtual. B is what is direct. So we always say this one is big and magnified. That's N. So that is all I can give you now. So with this, I know you are happy. We have this question that says that the focal length of a concave mirror is 2 centimeters. F is 2 centimeters. Then if an object is placed 8 centimeters from it, that is U equals 8 centimeters. The image is at where? V, image distance unknown. But all we know is that 1 over F equals 1 over U plus 1 over V. 1 over V here is equal to 1 over F minus 1 over U. That is to say, 1 over V equals what? Equals what am I doing here? I don't need this. 1 over V equals 1 all over 2 minus 1 all over 8. 1 over V is equal to 8 here. Here is 4 minus 1. 1 over V equals 3 over 8. V equals 8 over 3 centimeters, which is 2.67 centimeters. Now they say that a current of 20 amps, current equals 20 amps, flows through a cable of resistance 5 ohms. Calculate the electric power distributed, P unknown, but P is known to be I squared R, which is equal to 20 squared times 5, which is 400 times 5, and that is equal to 2000 watts, which is 2 kilowatts. Okay. record this thing. Let me record it. You see the focal length here, just like I solved it, that focal length is 2 centimeters. If an object of is 30 centimeters from here, the image is attached. So F is 2 centimeters, U is 8 centimeters, V equals unknown. But we know 1 over F equals 1 over U plus 1 over V. 1 over V equals 1 over F minus 1 over U. Doing that, it means that we have 1 over V equals 1 over 2 minus 1 over 8. If you do that, the LCM is 8. 2 in 8 is 4. 8 in 8 is 1. That's 3 over 8. So V equals 8 over 3. And that's 2.67 centimeters. Now, this last question just solved now is, okay, a current of 20 amps goes through a cable whose resistance is 5 ohms. Calculate the electric power. So that's one. I is 20 amps, R is 5 ohms, P power unknown. For P equals I squared R, which is 20 squared times 5, 400 times 5 is 2000 kilowatts. The last question solved now is an alternative circuit question that says that another source is connected in series with a capacitor of capacitive reactance. Capacitive reactance of 10 raised to power 3 root 3 ohms. And a resistor of resistance 10 raised to power 3 ohms. The impedance of the circuit is dash. So XC is 10 raised to power 3 root 3 ohms. The resistance is what? Is 10 raised to power 3 ohms. Again, so I didn't put the ohms there. I didn't put the ohms so that we can be happy. Ohms there. So this impedance is Z, that is unknown, which is the square root of R squared plus AC squared. So we have 10 raised to power 3 squared plus 10 raised to power 3 root 3 squared. That's 10 raised to power 6 plus 10 raised to power 6 times 3. We manipulate to get it there with 4 times 10 raised to power 6. Then we got 2 times 10 raised to power 3 ohms or 2000 ohms. Question, please. Question.
Strategy.
Yes.
Not that. What are we going to meet? That's light wave. I don't understand it.
Which
Don't you
one?
thought it was light
one?
wave? Usually rays, ray reflection and refraction. So I don't understand anything in that light wave.
Oh.
So she was just jumping, like was rushing this topic.
You mean the reflection?
Ray diagrams.
Ray diagrams. That's quite easy. Okay. Tomorrow morning is going to be tedious.
I'm having an exam tomorrow morning. And
What is
tomorrow
it?
by 3.
You
I'm
have
having an
it?
exam by 3. Yes.
Okay. You are suggesting whether we should meet tomorrow morning again. The problem I have is light. I'm just disturbing my neighbors there, using them every time. That's the problem I'm having. So I want to consider that. But what I think we can do, instead of meeting for that normal time, 6:30 a.m., very easy, disturbing somehow for some people.
Okay.
So I can shift it to 9. Would that
9 in the morning.
Convenient? Yes.
9 in the morning.
Yes.
Okay, sir. Okay, yeah. It's convenient.
Okay, no problem. So be it.
Thank you.
Okay. Any other question? But if you don't mind, I can still discuss it. Can we continue till
okay, then.
all done with Jamb? It depends on you people. It depends. Now, let me quickly discuss the aspect of the reflection. that you had issue with. So it's quite easy, really. So, like yesterday, I was discussing something. I've discussed the radius of curvature, many things discussed, really. Let me go to that place where I can still.
Sir,
yes.
9 o'clock is not convenient for me because my mom is going to take the phone by 8 because she's going to work. That's why I'm.
And when are you writing your examination? You can get the video at any
tomorrow.
time.
Tomorrow.
Tomorrow again? Who is that?
Temple.
When
tomorrow by 3. By 3.
The two of you writing the same time? I think Blessing said 3 now, right?
Yes.
The two of you.
Yes, by 3.
What are we going to do? Your mom will collect the phone by 8.
Maybe 8. Yes.
So what are we going to do now? Anyway, let me discuss this one and finish it so that any other question you have, you can send it to Telegram or send it to me directly. Then I will give it to you. Then Temple, don't forget to send your phone number so that I can send the YouTube straight to you since you are not in Telegram.
Sir.
Now I've explained the concave and convex of a thing. Then focal length explained, everything explained. Actually, principal axis is this line, these lines that combine the C, F, P together. How do you not draw a ray diagram? It has rule. Once you get the rule, that's the end. If you get the rule easily, that's the end of the whole thing. Now, how do you draw? The first rule that you must note is that rule of ray diagram. Rule of ray diagram. The first rule is that all ray parallel to the principal axis reflects back through the what? Through the principal focus. How do you draw that? Assuming you have this. This principal axis is an object. This principal focus. If an object is here and there is a ray from there parallel to the principal axis.
Is it eating tomato?
Temple, you are disturbing. Mute yourself. So when the ray is drawn, that's the first thing. A ray must be drawn parallel from the object. Then you draw it back through the principal focus. That's the first thing to be done. Second thing, all ray through the principal focus, just like opposite of what we did. Reflects parallel. Reflect parallel to the what? To the principal axis. If the ray now passes through the principal focus, it will reflect parallel to the principal axis. For instance, like this. You have the principal focus here. You must draw another ray passing through the principal focus like this. See the arrow is going down through it. Then you must draw it parallel, again parallel to this line, Then the third one is per absence, a ray through the center of curvature. Center of curvature. Reflect along its path. Its path. That is, it reflect back along that same line, same direction. That's on this. You see it. Center of curvature is there. Now see an image, something passing through that guy. It passes through the C, then it shorten it. That can go like this. It goes through C. It will reflect back along that line immediately. It will pass back. That is how to draw a diagram. We now combine all this together to give the diagram of anything you want to draw. Let me just give you like 2 or 3 diagrams. Now, the first one I want to do image, nature of image. Of the concave mirror. Concave mirror. Once I'm able to draw all this for you, you will get the meaning. Is that okay? Now this one here, we start with the first case is where this is. Number 1, if object is beyond C, that is, you have F here. Let me use focal length now. These 2F or either C. Okay, let me use the principal focus. And the object is here. The first thing you do ever is to draw a parallel line to this place. So the principal axis. And that parallel line will reflect back along F like this. Let me draw this thing to be longer or bigger to see. You see that? See that? So we now have another one that is drawn through the principal focus again. Then it will reflect back. Oh, diagram is totally wrong. Sorry about that. Let me just clean that one. Because something is not straight to my understanding. So let me straighten it well. It's drawn straight like this. Then that is the direction. It will reflect back parallel to the principal axis. You can see the way it reflects back. Where they now meet, you will draw your image down to it. with arrow towards the place of point of intersection. You can see the object here. See the size of the object. See the size of the image here. This is the O object here. This is the I image here. What does it give us? It gives us real image. Once the image is formed in front like this, in front like this, it's formed in front like this. You say it is real image. So we have real image. We use R for that. Then the image is pointing downward. It means it is inverted. Inverted I. Then at the same time, it is smaller than the object. You say it is diminished. At that point, you have, so we call this one read. Read. Number 2 is object. Oh, now image formed at where? Image formed. Oh, this thing is recorded. It's recorded. Thank God. Hey, it means 10 minutes. It means 10 minutes. Oh, sorry about that. Image formed between
C and F.
C and F. You can see that. Another one is object at C. When object is at C, what happens there? So we'll see it now. Tempo, 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 moves. So if object is placed at C, you first draw your parallel line to the principal axis. Then it reflects back along the line through F. You draw again through F. It reflects back to that place. The arrow back. Consider F is important here. So the image is downward here. The image is downward here. You will now see that the normal thing that happens here is that the image is formed in front where you have the mirror. The image is real image. R again is inverted I again, but it's same size. Same size. That's S, we call it race. So here, image formed at C again. Image formed at C. The next one, you have less than 8 minutes. Then objects between C and F. Between C and F. We have it like this. This F here, C here. Object is between C and F. First, parallel line to the principal axis passes through the F. Through F. Then another one is going through the F itself. It reflects back there. And they all meet. They met here. So what is that implication? The image is still real. Image R is still inverted. I, but it's now magnified. Image, see, look at the objects, look at the image. Is magnified, that is bigger. That is real. Here, image formed where? Beyond C. Image formed. You can see the correlation between the first one and the third one. When object is beyond C, is formed between C and F. Now, object is now between C and F, is formed beyond C. So they are like opposites. So you must get that right. Now let's look at object at F. Object at F. Object at F, yeah, if the object is here, we have this guy going this way, parallel. It reflects back along F. Now, another object, instead of it passing through the F, it can't pass through F now. It will pass through C. It pass through C. Sorry. Through C like this. It will pass through it. You know, I told you anything that passes through C will reflect back along this line. Reflect back like this. So passes through it like that, it reflects back in that line. So, and that is why you see the image can be seen here, but it's formed at the infinity. The image is still real. It's said to be inverted here, even though we can't see it because it's going down. We can't say that it is the magnifier. Nothing we can say about that. It's just RI here. Then image formed at infinity. The last one for this one, you go and master that of the, what's it called? That guy, the complex. It's just one. Give you virtual image, diminished, direct. That's always sure for that one. Let me now take the last one here, number 5. It remains just 1 minute 50 seconds. Objects between F and P I need to rush this one because of time. We have F here, P here. I didn't show PC. C here, object is here. So this guy here goes like this. Instead to pass through this guy like this, but it reflects backward. Backward. It appears at the back. Appears at the back. Outside there. Less than 1 minute. So this one also goes like this through C, or reflects. How I can join it together through C, or reflect backward like that. There, outside goes this way through C, or reflect backward like that. Then they met somewhere around here in front. There. So the image is visual. B is what is erect. So we always see this one is big and magnified. That's N. So that is all I can give you now. So with this, I know you are happy.